Welcome back my dear friends, a very good morning, good afternoon, good evening to all of you, and as you know this is the DADM course which is data analysis and decision making under the NPTEL MOOC series, and this course is for 12 weeks, 60 lectures, that is total combined hours being 30, and each week we have 5 lectures, each being of half an hour. So, we are in the 33rd lecture, and in the 32nd lecture if you remember we have just discussed very briefly that what is with an example for the multinomial model, that contraception example, and we drew the graph. Later on we went into mentioning what is the multinormal distribution for the p variable or k variable, and how it has a one to the in the formula sense, how is it has a one to one correspondence with the univariate normal distribution. And then we considered the bivariate normal distribution, wrote down the formulas, also considered the relationship between the two normal distributions, whether they are not related, whether they are related positively, whether they are related negatively. And we saw the contours which was looked like two looks like ellipse with a major and minus axis, and one looked like a circle, that the concentric circles. We are taking the slices looking from above. Then we considered the student T distribution. So, all these things are background, are giving the examples, and then how the student T distribution was exactly formed in the same way as the univariate student T distribution. Then we then very briefly I mentioned about Copula theory. I will come to Copula theory later on in details. And in Copula theory I did mention that at the extremes, whether high values or low values of x, the relationship at the extremes whether negative or positive between x and y need not be linear, they can be non-linear also. So, in order to basically consider that, we consider the Copula function, which is a function of the univariate distributions u1, u2, u3 till up, and each of them were basically uniform discrete distribution or continuous distribution, whatever the case, because continuous distribution is the best way, between 0 and 1, and Copula functions are very heavily used in order to find out the relationship at the extremes. So, continuing the Copula function, so they are used to describe the dependence between random variables x1 to xp. As per the fundamental theorem of Sklar, every distribution, every joint probability distribution. So, this is the joint probability distribution. Because it is no more an univariate, it is basically the relationship between x1 to xp. And the marginals are given. Marginals means the univariate cases of each as given for the x1, similarly x2, x3, x4 till the pth one. So, all of them are univariate normal for the marginals. So, in that case the joint probability distribution can be related by a Copula function, where the variables of the Copula functions are the marginals themselves. And what we will do is that later on see how the marginals can be converted using the univariate continuous case between 0 and 1. The concept is intuitively very simple. Now, for a univariate uniform continuous distribution between 0 and 1, the sum of the probability is always 1, which is true because the CDA value is 1. What you do is that you map that corresponding value 1 to basically consider the marginal, any marginal, it is fx1, fx2, fx3, where x1, x2, x3 all are normal distribution. So, obviously, that area is also 1. Now, depending on the value of x or depend x1, let me use the word x1, or depending on the value of u1, you can find a one to one correspondence between u1 and x1. So, you have different realized values of u1, you will have basically different realized values of x1. Similarly, you can have different realized values of x2 would have different realized values of u2. So, underlying fact remains that the CDF value for the normal case from 90 minus infinity to that value of x2 would be exactly equal to the CDF value sum of the probabilities for the uniform continuous case from 0 to that value which is u1 or u2 as the case may be. And then you can find out the Copula function. Now, these Copula functions are used to describe dependency between random variables x1 to xp. As per the fundamental theorem of Sklar, every distribution which is the joint distribution with marginals fx1 to fxp may be written using the Copula function. So, this is the Copula function which I just mentioned. So, you have the joint distribution of x1 to xp that is equal to the Copula function of the marginals. So, let me use a different color. So, this is the Copula function which you have, which you need to find, and these are the marginals. So, this is basically a function of the marginals being mapped onto the joint distribution. So, alternatively Copula function of, now what you do is that you convert these x1, x2, x3 distribution corresponding to the fact that the sum of the probabilities of all them is equal to 1, you map them onto the univariate case and do the problems accordingly. So, I will come with the diagrams and all these things later on. So, let me write it and explain. So, consider you have a uniform continuous case between 0 and 1. The 0, the axis I have shifted out to the left. So, this CDF value is exactly equal to 1. So, the sum is 1. Now, consider in the other case you have another distribution and that is normal. So, this is normal. So, this distribution value is also 1. Now, I need to do a one-to-one correspondence between them. So, one-to-one correspondence between these two distributions. So, what I do is that so I will write in let me use another color, let me use the blue one. Yeah. So, the integration from minus infinity to a, so I will use a blue color here in order to highlight. So, consider this value, consider a value here. So, these are corresponding values and I am basically trying to map these two values for equivalence. What I mean by equivalence, I am going to come to that. This color should be same, yes. So, these values of the CDF addition should be exactly equal to this. Right. So, this is done. Now, what do we do? And use this one. So, consider this value is, I am writing in blue. So, it will, the color difference will make you understand. This is x1, this value is here would be, say for example, u1. So, x1 f of x1 dx1 will be equal to summation for probability of u1, this is the random variables. So, this is a random variable capital, this is capital, is less than or equal to u1. So, this part, if we use green color, yes. So, this part and this part are equivalent, which means if I take the color, the overall formula which is given here and the area which you had here would be exactly same. Point 1, point number 2, this part and this part are again equivalent, but there is equivalence in the sense the total area is same. So, I think so this part and this part area wise they are same. So, you use the equivalence and basically find it out. So, that generally we use for generating pseudo random numbers in the computer. So, that is basically the general essence. So, very simply to illustrate the application of multivariate T distribution, let us consider the following two scripts. One is Tata Steel, one is SBI from the National Stock Exchange, date being 1st of January 2015 to 29th May 2015, and we take the data from NSE India. So, it can be found in Yahoo, Google, whatever, but I am taking the end of the day price. So, if you draw the two dimensional copula considering a bivariate T distributions, considering the returns would be given by Neperian log base E of the today's price divided by yesterday's price. So, if I am that return would be given for yesterday. So, if I want to find out the return for today, it will be the log base E to the, and the ratios of the prices would be tomorrow's price by today's price. So, that is basically the return of today. So, we find out the returns in this way of all the these two pairs of stocks, and then based on that one can find. So, before solving that problem, let me mention that one can find out the mean values for both the stocks, the standard deviation of both the stocks, the covariance of those stocks, but here we try to basically use the student T distribution. So, we use the Copula function using the student T distribution. So, here now you see very interestingly I am using Copula functions also plus the bivariate student T distribution. So, I am trying to basically use the concept which I have just covered in trying to highlight how they can be used. I am not going to the details of the calculations, just the flavor. So, the PDF, because student T distribution if you remember or is basically a continuous case, and for your obviously you would have understood by this now the chi-square, f and t and z all are continuous distributions. So, if we along the x axis we plot Tata Steel, along y axis we plot SBI, and we get the PDF for the student T distribution on the using the Copula functions. This is the concept of the bivariate T distributions using Copula. So, these are the values, and if you see that at the extremes when both the in the univariate case obviously you have converted into univariate case, at the extremes means at the value of 0 for the SBI and 0 for the Tata Steel, or 0 for the SBI, 1 value. These are the univariate conversions which I am talking about. So, obviously the univariate student T distribution for SBI would be converted to a univariate continuous case between 0 and 1, similarly for Tata Steel. So, I am considering the relationship between SBI and Tata Steel at their extremes. So, rather than talking about the extremes, I will talk about the point 0 0, 0 1, 1 0, 1 1. So, you see these values at the value of 0 0. This is the relationship at the value of SBI and Tata Steel. So, we basically SBI being 1 and Tata Steel being 0, and Tata Steel being 1, SBI being 0, and the final for both the values of 1 1. So, you find at the extremes the actual concept of the Copula comes into the picture in the right way. So, I will mention few coefficient relationship, these are not immediately important, we will see that as we proceed. The Pearson correlation coefficient between the two scripts can be found out. So, the Pearson correlation coefficient is exactly like the correlation coefficient which we do. So, obviously, the principal diagonal will be 1 1 and of the diagonal element value is 0.35, which means the correlation coefficient existing between these stocks is about 0.35. Now, then we come to the Wishart distribution is basically a generalized. So, if you remember, I am going in a very scientific manner for the univariate normal, then I discuss the p-variate multivariate normal distribution. Then you have initially you had the student T distribution, then I discussed the multivariate student T distribution. Initially you had the chi-square of all these are the univariate chi-square, then I am going to discuss the multivariate chi-square which is the Wishart distribution. The Wishart distribution is a generalized of the chi-square distribution in the multi-dimensional case or multiple dimension. It was first formulated by John Wishart. So, hence we are basically given the distribution as such. So, suppose x k, so generally we will consider x k as being 1, 2, 3, 4 to v, which is basically the degrees of freedom. So, in that case you will have the Wishart distribution given as the multiplication of x k and k, which are basically normal with certain mean and certain standard deviation, which is the covariance variance matrix. So, here the covariance variance matrix would be size of p cross p and it will be a positive definite, while the value of v would definitely be greater than p minus 1 and you can solve the problems accordingly. So, this would be the degrees of freedom. The Wishart distribution arises as the distribution of the sample covariance matrix for a sample from a multivariate normal distribution. So, as if you remember the chi-square used to come out for the case when we are going to discuss something to do with the standard deviation. So, it will be chi-square with n degrees of freedom, chi-square with n minus 1 degree of freedom. Similarly, the Wishart distribution will be rising for the case when you want to basically study something to do with the covariance matrix for the multi-normal distributions. In the similar way, one to one simile you can see and similarity. Then the Wishart distributions basic it would basic if n is a matrix of n cross p, where n is the number of readings, p is the number of random variables, then the Wishart distribution would be given by the formula which is here. So, this is the trace, TR is the trace, and given this formula, these are very simple. This p is the number of random variables, this is the gamma distribution value, this is the variance covariance matrix, p as I discussed is the number of random variables, v is basically the degrees of freedom. So, all these things are known to us. Now, we will consider the inverse Wishart distribution. Inverse Wishart distribution is denoted by IW. So, W was for the Wishart distribution, IW would be the inverse Wishart distribution and the suffix P or K would denote the number of random variables which are independent. It is the multivariate it is again in the univariate case you have the simple inverse gamma function. So, the extension of the inverse gamma function in the multivariate case would basically be the inverse Wishart distribution. If one considers that the Wishart distribution generates the sum of the squares matrices, then the inverse Wishart distribution can be imagined as that which generates a random covariance matrices based on which we do our studies. So, inverse gamma distribution, inverse Wishart distribution have again similarity in the univariate and the multivariate case. So, in this case if W is Wishart distribution with degrees of freedom V and the variance covariance matrix even, then the inverse Wishart distribution would also have the same degrees of freedom and the other parameter rather being the covariance matrix, covariance matrix, it would be the inverse of the variance covariance matrix. So, user inverse Wishart distribution can be found in Bayesian statistics, where it is used as a prior on the variance covariance matrix of rho of a multivariate normal distribution, and based on that we do the studies. So, remember that for the multivariate case one can make deductions about the Wishart distributions and inverse Wishart distributions in a similar manner as we can do for the chi-square and the inverse chi-square, which is done in the univariate case. So, Wishart distributions or the inverse Wishart distributions would basically be in the counterpart from the univariate case would be the chi-square and the inverse chi-square distribution, and we will try to basically see that through the diagram. So, this is the Wishart and the inverse Wishart distributions is being considered. Here illustration is basically through the chi-square with v degrees of freedom. So, chi-square with 1 degrees of freedom is this pink one, and this is x axis is the chi-square, along the y axis you have the density. Then you have 3 degrees of freedom, 6 degrees of freedom. So, this is for 3 and this is for 6 degrees of freedom based on which we draw. So, this is the univariate chi-square. So, obviously, you can, if you are able to draw for the higher dimension, you will get the Wishart distribution, because you remember the one-to-one similarity. When we have the inverse, for the univariate case you have the inverse Wishart distribution, again degrees of freedom being 1 or 3 or 6 using the pink, blue and green line. You will basically have the inverse Wishart distribution, inverse chi-square distribution, which is the counterpart in the univariate case for the inverse Wishart distribution, and again you can draw it accordingly. Again along the x axis you have inverse chi-square, and along the y axis you have the density plots. Now, we will, so again I am repeating this, just a thorough way of trying to basically give you a feel what things are there. So, multivariate extreme values give us the picture of an asymptotic behavior of the components wise based on the maximum and the minimum for our IID. So, the main problem one faces is how to define multivariate extreme value distribution, which is MEVD, multivariate extreme value distribution. This problem arises due to the fact that there does not exist any strict ordering principle for the multivariate observation. So, if the problem is, if x1 in univariate case is very simple to basically rank them from the lowest to the highest. But say for example, when I am doing for the multivariate case, it may be possible the random variables x1s are ranked, but the random variables x2 values are not possible to rank, because they are basically not ordered. Similarly, when you try to do it for the x2, rank them, it may happen that in the moment you do that, x1 is not ranked or ordered. So, trying to basically have an uniform ranking system for x1 to xp is not possible in the multi-dimensional extreme value case. So, let us assume y being IID and we want to basically find out the maximum of them, and you have basically p number of random variables and each has n number of readings. Now, as per the definition, as n is the number of observations which I have just mentioned, while p is the dimension of that random variables. So, consider p1, p2, p3 till p means p value 1, 2, 3, 4 till 10. So, you have 10 number of random variables, each has basically n readings. So, given this, we are interested to find out the maxima. So, what you are trying to do is that we, in a very simple case without going to the details of the formula, consider you have a univariate case. So, this example if I give, hopefully it will make things clear to you. So, consider a data set is there, let me try to make it, wait, it is possible. So, consider you have a data set and the values are marked x1 till x, say for example, capital N, whatever the values, forget about that. Now, what I do is that I break that into groups, same number, and consider the groups are given as number, first one, second, third, and so on and so forth. Now, in the extreme value case, what I will do, in the first case, let the values be, the first one be the group number 1, second one be the reading number till, say for example, 1 till, say for example, n. This n and the other value of sample size, let us not confuse. So, what I do is that I find out the minimum. Similarly, find out, I take the minimum of x2, this is the first 2 is the so called block number, second one is the reading number till x2n. I continue doing it for the last one, give our value x n1, x nn. So, once I have the means, I jumble them up. Jumble them up, so consider I keep it in a box. So, in the box what are there? They are the means of the minimum of different blocks which I have taken. Now, consider I am able to take them as take the minimum of that minimum and continue doing it for such different number of n values. So, it may be possible that the minimum of the minimum for each block would actually give you the realized values of the sample of the minimum distribution based on which I am trying to find out the extreme value for the minimum. Similarly, if I do for the maximum value, I repeat it, take the blocks, find the maximum for the first block, for the second block, third block, put it in a box and then find out the maximum of the maximum. So, if I do such different type of blocks and I take it 1 time, 2 time, 3 time, then the realized values of the maximum would actually be from the sample based on which you are trying to find out the extreme value distribution. So, these type of bootstrapping, so called bootstrapping, other things can be discussed in details if somebody has a good knowledge in statistics, and they are very heavily used in data analysis nowadays, like the concept of bootstrapping, concept of time series, concept of Bayesian analysis, they are being very heavily utilized. So, we will cover them later on, but let us proceed slowly and try to basically understand the concept in a much better sense. With this, I will close this class and hope all of you are finding it interesting, and have a nice day, and thank you very much.